This is the second lecture from Chapter 15, and this particular lecture focuses on comparing what we call the reaction quotient Q to K, the equilibrium constant, and then discusses a conceptual theory called Le Chatelier's principle. If you were following a chemical reaction and you wanted to know when it was at equilibrium, how would you go about doing that? You would need some way to collect data and then compare that to the equilibrium constant that hopefully had been established for that reaction. Well, that data that is collected to compare is usually put into a formula called Q, the reaction quotient. The mathematical formula for Q is the exact same as it is for K. So it's concentration of products raised to the power of their coefficients divided by concentration of reactants raised to the power of their coefficients. The difference between Q and K is that the concentrations used to calculate Q are the concentrations of reactants and products at any point in the reaction. Remember that when you're calculating K, the equilibrium constant, the concentrations must be those that exist at equilibrium only. So the whole purpose of Q is to tell us whether or not we have in fact reached equilibrium, and if not, in which direction the reaction must go, left or right, that is towards reactants or products, in order to reach equilibrium. So let's take each of the scenarios one at a time. If Q equals K, clearly the system is at equilibrium, okay? If the number you calculate for Q is identical to the established number for K, you are at equilibrium. All right, if Q is greater than K, let's think about what that means. So the mathematical formula for Q and K, both products over reactants, right? So if Q is greater than K, another way of saying that is if Q is too large, okay, what does that mean? That means that there's too much product, okay? The numerator is too large. And if there's too much product, in order to reach equilibrium, the reaction will need to shift to the left, okay? That means remember, to the left is reactant. You'll need to shift to the left to make more reactant and less product. If Q is less than K, what does that mean? Well, again, looking at the expression for Q and K, products over reactants, if this ratio is too small, Q is less than K, what does that mean? That means there's not enough product, okay? There's not enough product. And so in order to reach equilibrium, the reaction would need to shift to the right to make more product. This is kind of a little memory trick that helps you remember how to handle Q and K if you're one of those people that feels like you're in a house of mirrors trying to figure out what's what. If this confuses you, please just skip it, but if it's helpful, that's awesome. And the technique here is that you set up a number line, just like imagine it's a ruler, where the small numbers are on the left, okay, and the larger numbers are on the right. And then make a little tick mark on that number line where your values of the equilibrium constant are and where your calculated value for Q is. Now, the objective is always to start at Q and get it to equal or go to K. So if you have the value set up in a number line, whatever direction you need to move to take Q to K is the direction the reaction also needs to move. So in this case, we have to move Q to the left to reach K. So that would mean the reaction will also have to shift left to reach equilibrium. So here would be a typical multiple choice type question that you might see applying this concept. So you might well get a chemical reaction, and you probably would be given the value of KEQ, that's just equilibrium constant. And then you might be given either concentrations of reactants and products at a certain time in the reaction, and have to calculate them. So let's say that you were given the concentration of 0.01 for the product and 0.03 for the reactant, and asked to predict which way the reaction would shift to reach equilibrium. The first thing you would have to do is calculate Q, okay, products over reactants. When you're plugging in the values for concentrations, don't forget your coefficients, okay, so this 0.03 has to be squared. Once you get the value for Q, you then compare it to K. So in this case, Q is 0.11 and K, as they told us, is 0.45. So obviously 0.11 is less than 0.45. So you would say Q is too small, okay? Which means products, which are on the top of the equation, are not enough. You need to make more product, which means you shift right or shift toward product. So that's the type of procedure you would typically go through to answer one of these questions. Here's one for you to try. So my recommendation would be to turn off the video and work this out, and then on the next slide I will discuss the answer. Alrighty, so anytime a question says which direction will reaction go to reach equilibrium, that's a Q problem, Q versus K problem. So what you're going to do first is take the concentrations they give you, and you're going to plug them in the expression for Q. Now, when you're working this type of problem as a free response problem and you need to show your work, you make sure you write out the generic expression for Q first, because probably the most common mistake students make is they forget their exponents. Or even if they remember their exponents, like I did here, they forget to actually use them. So if you remember to cube your 0.8, the value you'll get here is actually 12.8. Anyway, so the value of Q is 12.8, and now you compare it to K. So Q versus K, Q is 12.8. K, which they gave us, is 5.67. So Q is greater than K. So that means Q is too large. That means the numerator, the products, are too much. So too much product, which means we need to move away from products or shift left in order to reach equilibrium. Alrighty, so as you remember, we learned about equilibrium, I hope. Once you reach equilibrium, the reaction does not stop. That's why it's called dynamic equilibrium. So the forward and reverse reactions are still going at the same equal rates, but there's no observable change in the concentration of reactants and products. However, if you do anything to disturb an equilibrium, and I'll tell you the 3 basic ways you can do that, the reaction will always respond by reestablishing equilibrium. In other words, the reaction will try to undo whatever you just did to it. So the 3 primary ways that you can disturb a reaction at equilibrium are by changing the concentration of any of the reactants or products, or changing the pressure, and that's only if you have a gas present. And just a reminder here, pressure is directly related to concentration. So when a problem is discussing pressure of a gas, you can think in your mind concentration. They have the same type of behavior. Or if you change temperature. Now I'm going to repeat the following a number of times throughout the equilibrium chapters, but the equilibrium constant is a constant always unless you change temperature. So listen carefully to this. Anytime you change concentration or pressure or anything but temperature, The reaction will shift around, but the equilibrium constant does not change, okay? Only when you change temperature will the equilibrium constant change. So we'll talk about each of these three ways to disturb an equilibrium one at a time. And so let's talk about if you change the concentration. Remember what I said about Le Chatelier. I said that whatever you do to it, the reaction will respond by trying to undo what you did. So let's look at some scenarios here. Let's say we have this reaction and we increase the concentration of one of the reactants. We'll just say B. We dump in more B. So we just added more B. So according to Le Chatelier, the reaction's going to try to undo what you just did. It's going to try to get rid of the extra B that you just added. How does it get rid of B? It shifts to the right to make more product, and that'll consume B. Okay, so the bottom line, if you want a summary statement, anytime you add reactant, okay, so anytime you add reactant, the reaction will shift right to get rid of that extra reactant. Now let's look at the reverse situation. Let's say that we add more product, that we dump in more C or D. Again, the reaction is going to respond by trying to get rid of that extra product. And how does it do that? In this case, it's going to shift left toward reactant to get rid of the extra product you just added. Now here's can be the trickiest one, so try to listen carefully, make sure you understand this. Instead of adding a reactant, what if I'm standing at a reaction vessel and actually removing one of the products as it's formed? What effect will that have? Well, the reaction as a whole will suddenly feel a decrease in product. So it's going to try to replenish that decrease. How does the reaction make more product? It shifts right. Okay? So again, the generic statement is if you remove product, the reaction will shift right. Here's one for you. Put the video on pause and think through how you would answer this question, and then we'll talk about it on the next slide. So in this case, you have to remember that pressure is directly related to concentration. So when you read a problem to do with pressure, again, think concentration. So basically what they're saying is if you increase the concentration or pressure of SO3, which way will it shift? And the answer is to the right, towards product. So it's okay to either say it'll shift right or it'll shift toward product. Each answer is perfectly acceptable. All right, so this one is the hardest conceptually to grasp, okay? So if you were in my live lecture, you know that. So you may have to listen to this a couple times and think through it privately, or perhaps go to the textbook and read it, but it may be a little bit of a tricky concept for you. All right, so again, if you impose a pressure change or a volume change on a chemical reaction, it will only have an effect if you have any gases. Now, all of the reactants products don't have to be gases. Even if just one of them is a gas, a change in volume or pressure will affect it. All right, so let's look at, often the problems are stated in terms of volume rather than pressure. So let's look at this scenario. What are we doing to volume? Okay, so we are decreasing volume in all of these. What does that do to pressure? Well, I'm hoping you're following still. If you decrease volume, if you scrunch all these same molecules down into a smaller space, pressure is going to increase, right? Pressure is due to collisions of gas molecules against the container. So obviously there are going to be more collisions if they're crowded. All right, so pressure goes up. So now we're going to think of pressure as concentration, right? Directly related. So if pressure goes up, that's like concentration going up. How is the reaction going to respond? Well, it's going to, Like, is it going to go left, right, what? We can't really say. It depends on the reaction. However, it is going to move in the direction that reduces pressure. It's going to move in the direction that reduces pressure, okay, because it wants to undo what just happened to it. How do you reduce pressure in a chemical reaction? You can't mess with the volume again. You only have the molecules to deal with. Well, to reduce pressure, you want to move to the side of the reaction that has the fewest gas molecules. So let's look at an example. Let's look at part A. If we increase the volume, so let's say we started with the volume like this, and we increase the volume so that these same number of gas molecules now have a lot more space. Okay, so volume has gone up, that means pressure has gone down. So what does Le Chatelier do to respond? He wants to undo what happened. He wants to do the reverse. So Le Chatelier wants the pressure to go up. How do you make pressure go up in a chemical reaction? You move to the side that increases pressure. Move to the side that increases pressure, and that is the side with more gas molecules. Okay, so let's go ahead and look at this reaction and count the gas molecules on the reactant and product side. So everything's a gas in this reaction. That won't always be the case, so pay close attention to the phases. So we have 2 plus 1. We have 3 gas molecules on the product side, and we have only 2 gas molecules on the reactant side. So remember, I actually write all this down or I get confused where I'm at. Le Chatelier wants to increase pressure, so it wants to move to the side with more gas molecules. So in this case, it's going to shift right because the right has 3 gas molecules versus 2 on the left. Okay, so it should be the opposite for the other one, right? Decreasing the volume, we hope, would make it shift to the left, but let's just verify that. So now we're starting with a large volume, spread out molecules, and we're going to squish it. So those same number of molecules are crowded and have more collisions. So what have we done to volume? We have decreased volume. What has that caused as far as pressure? It has caused pressure to go up. So then Le Chatelier wants to respond by doing the opposite. In other words, it wants pressure to go down. And now how do you make pressure go down? You move to the side with fewer gas molecules. Okay, and which side of this reaction has fewer gas molecules? The left. So that matches up okay. So here it is in written form instead of my oral form, in case you want to jot down any notes. Alrighty, this is just a little tidbit that I've often seen show up on the ACS final, and I just want to make sure you stored it away someplace. If you add a gas that has nothing to do with the chemical reaction, it's not a reactant or product, and it doesn't react with anything, that's what inert means. So you add a gas that doesn't react with anything, it will have no effect on the equilibrium. There will be no shift left or right, no Le Chatelier response. So you might think, well, why is that? Because if you add another gas, you increase pressure, right? Well, you do increase pressure, but you have not affected the pressure that your reactant and product gases exert. All gases can coexist without affecting each other. So don't get lulled into that. Just remember, if a gas is added that has nothing to do with the reaction, there is no shift, there's no response. Alrighty. The last way to significantly affect the reaction and have a Le Chatelier response is to change the temperature. Now remember what I've been hopefully drilling in your head is that a change in temperature is the only way that you will see a change in the equilibrium constant. So if you have a temperature problem, not only do you need to predict which way the reaction will shift, you also need to predict what will happen to the equilibrium constant K, because it will change. So which way the reaction will shift depends on whether or not the reaction is exothermic, which means it gives off heat, or endothermic, which means it must absorb heat in order to proceed. If you understand the following concept, dealing with temperature changes are very easy. If you have an exothermic reaction, which means the reaction gives off heat, you literally write in heat as a product. Heat is given off, it's produced, so it really is a product. So literally write it in as a product and treat it like any other product if you were trying to figure out what would happen in Le Chatelier. So let's look at an exothermic reaction. We have heat written in as a product, and let's say that the problem tells you what happens when you add heat to this reaction. Well, heat we're going to treat like a product because it's exothermic. So if you, like any product, if you increase the amount, the reaction will shift away from it to try to get rid of that extra heat you just added. So it's going to shift left. If, on the other hand, you remove heat, now how do you remove heat? Typically, the wording of the problem will say you cool it down. Okay, cooling is just removing heat. So if you remove heat, that's like removing a product. Okay, and Le Chatelier says the reaction is going to respond by trying to replenish that heat that you just removed. Which way does it shift to generate heat? To the right. Okay, towards product. All right, almost done with this lecture. Let's look at the same type of scenario, but for an endothermic reaction. An endothermic reaction is one that must absorb or take in heat in order to occur. So heat in an endothermic reaction is treated like a reactant. You literally write it in and then again treat it just like you would any other reactant. So if you have established that you have an endothermic reaction and you're told what or asked what happens when you heat it up, if you heat up an endothermic reaction, Le Chatelier responds by trying to get rid of that heat you just added, and it does that by shifting to the right, away from that heat, so toward the product. So endothermic reactions respond totally opposite to exothermic with heat. Again, if you have an endothermic reaction and you remove heat, if you cool it down, Le Chatelier responds by shifting towards reactants to replenish that heat that you are removing. All right, so I told you if you're talking about changing temperature in a reaction, not only do you need to think through the Le Chatelier effect, you also need to think through what will happen to the equilibrium constant, because equilibrium constants do change with changes in temperature. So all you have to do is look at which way the reaction shifted in order to determine what happens to K. If a reaction shifts left, this is only with a temperature change. If it shifts left, what does that mean? It means you're reducing the amount of product you have. If you have less product, what happens to K? Now remember, K is product over reactant. So if you have less product, that means your numerator is getting smaller. K gets smaller. K decreases. Again, please make a note of the change in K is only seen with changes in temperature. If you have changes in concentration or pressure and it causes a shift left or right, the concentrations will adjust themselves so that there's no net change in K. So don't get this mixed up. All right, similarly speaking, if you have decided with a temperature change that the reaction will shift right towards product, that means you're making more product. If you look at the expression for K, if you're increasing product, which is the numerator, you're also increasing K. Same type of scenario for an endothermic reaction. Walk yourself through, make sure you can go through this prediction process. It can get confusing. Jot down stepwise what's going on if that helps you. But again, look at the way that the reaction is shifting, and then K does the same thing as the reaction. Again, these are only for temperature changes that K will be affected. All right, and finally, just a tidbit last minute factual slide again that you might be asked, and that's the effect of a catalyst on the equilibrium. Bottom line is a catalyst does not affect equilibrium, okay? You remember the definition of a catalyst, it's simply something that speeds up the reaction without being consumed. Well, a catalyst will speed up the forward and the reversed reaction, and so there's no net change. So catalyst does not affect the value of the equilibrium constant. That is it for the second lecture.